Okay, so let's see. Let's do first a numeric example, a short numeric example with the rocket equation, just to get an idea of some magnitudes that are involved in here, and then we're going to, I said in the beginning of the class, we're going to take a step back and revisit both the momentum equation and Bernoulli's equation. So we're going to discuss more about the Bernoulli's equation right after this example. So we have a single-stage rocket, which uses a liquid oxygen kerosene propellant. It has a specific impulse of 3,200 meters per second. Remember, specific impulse was this term, let's call it IS for the specific impulse. It was this term that appeared in the rocket equation, which was the thrust over m dot. And we're given this here for this particular rocket, 3,200 meters per second. And what would be the ratio of propellant mass to total initial mass to achieve orbital velocity? Orbital velocity for an Earth satellite, it's in the order of 7,600 meters per second. So this is what we need to obtain in the rocket. So how do we solve this? We have the rocket equation we've just obtained previously is equal to this specific impulse times the logarithm of initial mass over the final mass. So we could, of course, turn this around and write m initial over m final is equal to the exponential function of v of the rocket over this specific impulse. And these things are given for this example, so mi over mf is equal to the exponential of the velocity of the rocket. Well, the rocket has to reach orbital velocity, right? So we want the velocity of the rocket to be at least 7,600 meters per second, and the specific impulse is given 3,200. So this is just a number here. We put it in the calculator and we obtain, what was it? 10.7 is the number I obtained. Okay, but the question is, what would be the ratio of propellant mass to total initial mass? So the propellant mass let's call it MP, has to be the difference between the initial mass and the final mass of the whole rocket plus propellant system, right? So M initial minus M final. Okay, so if what we want really is the ratio between propellant mass to total mass. So total mass initial, Mi. So that is equal to, so let's just divide this equation by Mi. If I divide this equation by Mi, I get 1. Mi over Mi is 1, minus M final over M initial, which is already obtained. Well, the inverse of that is already obtained, so we can calculate here 1 over 10.7 from our previous result. Yes, good. And then now again we can put these numbers in the calculator and get 0.906. So what does that seem like to you? It's a pretty large proportion, isn't it? So this is what happens, right? With a single stage rocket, a very large fraction of the initial mass must be propellant, or the fuel, basically, call it the propellant, to achieve the orbital speed. which is the reason why we have multi-stage rockets. Multi-stage rockets improve the payload capacity because basically the fraction that is left here, which is less than 10%, has to be, you know, the payload, the leftover structure or whatever rocket, the actual rocket, right, structure and the payload cannot be more than 10% of the total weight. So that's very small. So when we have a multi-stage rocket, we improve that capacity for payload because we have separate tanks which carry propeller, and each tank is discarded once the propeller runs out. Sometimes even each one of those stages will have its own engine, and the whole thing is discarded when it runs out, so that we don't have to spend any energy accelerating that empty tank any longer. So the whole thing is, each stage is discarded, and so each new stage has a much smaller rocket to accelerate, in other words. And if you add this up, then you get an increase. But it's a very tricky business here to find the exact, you know, to find the optimum situation. I wanted to continue now with revisiting the Bernoulli equation. And we must be aware that it is very easy to misinterpret Bernoulli's equation. We've applied it, we've learned how to use it, you used it in your lab, we've kind of gotten the hang of it, but now I want to go back and discuss a little bit more rigorously the Bernoulli equation, because in fact there's a lot of common applications of Bernoulli's equation to explain things like the generation of lift on an airplane wing, which are actually wrong. And you can find some very interesting articles and discussions about this. And in fact, let me show you again on Blackboard. I've put some of these links that you might be interested in reading. One of this describes the misinterpretation. One of this is quite a sort of renowned online publication by Professors Weltner and Engelmann Sundberg, if I pronounce that correctly, in Frankfurt. And they explain how the common derivation of Bernoulli's equation using just energy considerations actually is misleading, and how Bernoulli's equation is used to explain things like the flight, or this typical example, this typical sort of demonstration of a ping pong ball being suspended in a jet of air, say with a hairdryer or something like that. I don't know if you've seen that. It's a very typical demonstration, and people explain it using the Bernoulli equation. It's actually not quite correct. And so one has to be careful with these interpretations. The equation itself is perfectly correct. It's just the interpretation that sometimes people make that is, well, just plain wrong sometimes. So for that reason, I think it is important that we look at the proper derivation of Bernoulli's equation. So let's consider 2D motion in steady flow. So for example, consider that we may have just an airfoil. Suppose, right, let me see if I can draw an airfoil. Okay, that's not bad. And let's consider a streamline that is passing over this airfoil. Oh, that was a little bit crooked, but there you are. That's a streamline. Remember, the definition of a streamline is a line that is always tangent to the velocity vector. Okay, so what we're going to do is consider a coordinate system which is based on the streamlines. So on one streamline, we will have one coordinate which we call, say, S, which goes along the streamline. S will start, suppose this is the initial time t equals to 0 here, and the coordinate S goes along the streamline, and the other coordinate would be in the opposite direction. Let me change to red so that it's not. The other coordinate will go orthogonal, of course, to S, and we call it N. So we have two coordinates, curvilinear coordinate system based on the streamlines for steady flow. For steady flow, when I look at the flow at different points in time, the streamlines are going to be always there in the same place. So I'm going to construct a coordinate system on top of the streamlines. So let's call then this S, which is a function of time, the distance along a streamline. Let's call V our speed, and the speed is going to be ds dt. Remember that the velocity is always tangential to the streamlines, and so the velocity really has only one component on this coordinate system, only the streamline direction, by definition. So V is equal to ds dt, the fluid particle speed. Any fluid particle has a speed which is ds dt. Let's consider, in addition, some sort of radius, because this is a curved streamline. So let's consider the radius of curvature of the streamline. And finally, n is our coordinate normal, in the normal direction to the streamline. The acceleration with respect to these streamline coordinates let's call it A, is equal to, well, acceleration by definition, dv dt, right? dv dt. In general, this could have two components, a component in the streamlines direction and in the normal direction. These are our coordinate system, curvilinear coordinates, S and N. The component of this acceleration along a streamline, so two components, one normal and one tangent, is AS, of course. This is dv dt. V is defined up here. V is ds dt. So recall that V is really a function of S, and so we use the chain rule to write dv ds times ds dt. And ds dt is V again, so this is just dv dt times V. Yes, thank you. Thanks very much. Okay, so now the component of acceleration normal. To a streamline is basically centrifugal acceleration. So if you have a streamline, let's do it in green, a streamline like that, and there's some radius of curvature, a large radius of curvature, so I've done that little wiggle to indicate that this is a larger thing, and I've just drawn it sort of squished, the radius R, that's the local radius of curvature of the streamline. Suppose we have a little element of fluid here, and that is the radius of curvature of the streamline. So the normal acceleration is just centrifugal acceleration, so A normal is V squared over R. So that's a very unreadable square. Basically centrifugal acceleration. So now what we're going to do is apply Newton's law. This is the proper way of deriving Bernoulli's equation. Newton's law along a streamline. So basically just force equals mass times acceleration. That's all we're going to do. But we're going to look at a small element of fluid like this one that I've drawn here, and a little cube-shaped thing that is oriented with the streamline, and we're going to do the components of force in the S direction and the N direction. Okay? Are you ready for that? Okay. Let's consider, I'm going to draw this element of fluid again, but I'm going to make it larger because so I can indicate some things. This is actually an infinitesimal element of fluid, but I'm just magnifying it a lot because otherwise I can't draw the things I need to draw around it. So there's a streamline passing through, and I'm going to call the dimension of this little block in the streamline's direction delta S, the dimension of this little block in the normal direction to the streamline delta N. And let's see, what's my coordinate system? I have a X, Y, Z, and so Y is normal to the page, and so the element of fluid has volume ds, dn, dy, y perpendicular to the page again, and we do sum of streamwise forces. I'm going to use the delta to indicate that this is still a very small, everything small, everything infinitesimal at this point, and the little s indicates it's in the streamwise direction. That is equal to the mass of this fluid element times the acceleration in the streamwise direction, which we've already calculated, and so that's mass, differential of mass is a small infinitesimal mass, and we had v dv ds. That is our acceleration in the streamwise direction. So let's write for that dm rho times the volume is ds, dn, dy. Don't have much space here. V, oh no. I'm just going to squish things a bit here. Rho, ds, dn, dy, v, dv, ds. I made it fit. Good. Now, the component of weight in the streamwise direction, because weight of the fluid element is pointing, you can't change gravity, it's always going to point vertically downwards. Let's consider this may have an angle. The tangential point here has an angle theta, and so the component of weight in the tangential direction is, tangential in the streamwise is delta weight in the streamwise direction is minus, because weight is, so let's see that the two components are going to be that and that in terms of vectors, so it's going to in the opposite direction, the negative s direction, so minus delta of weight times the sine of theta. Yes, you have a question?
Y is perpendicular to the ns, right? Is y coming out of the
Y is actually going in the page, but is it, let me see. That works? Yeah, that works. In the page. But dy is just a dimension, right?
Yeah.
Okay, it's the width into the page. So we have the weight, and we have the sum of forces, and that's it, right? Oh, we could have pressure forces as well. So now pressure forces requires us to do a little bit of work. But let's look at so this is going to be basically a pressure with respect, this is going to be a function of both the streamwise and the normal direction. And so now we're going to have to do a little bit of math. I hope you're ready for this. Taylor expansions. Oh. Hold your seats there. No, nobody run. Nobody. Taylor expansion of pressure at the center. So P is going to be the pressure at the center of the fluid element. And let me draw this a little even bigger here. I'm going to keep my color scheme. I saw your hand, Nathan. Let me just draw my little picture. And I'm going to use red for the pressures. We have pressures on every side of this element, but pressure here is P, and we're going to use Taylor expansions, and there's going to be a dP, there's going to be a dP in the S direction and a dP in the N direction. And so, for example, dPs, the change in P in the S direction is the partial derivative of P with respect to S times, from here to there, we're moving only ds half, because we're looking at the pressure at the center. So times ds half. Also, in the normal direction, we would have dP normal is equal to dP dN times dN half. You had a question? We're looking at the sum of forces in the streamwise direction. We'll do the normal direction afterwards. So, because we're moving from here to there, from the center to the pressure acts in this face of the fluid element. The whole distance from edge to edge is dN in the normal direction and the S in the streamwise direction, but from the center to the face it's only ds half and dN half. So we're going to write the pressures in this form. Let's write the pressures, and so that becomes a little bit more clear. This is going to be P plus the differential of P in the normal direction times the area that this pressure is acting on. The area that this pressure is acting on is ds dy. That's the force due to the pressure there. On the other side, we have P minus dP normal. This is the way I'm doing the Taylor expansion, applying here to the pressure, times the area that this pressure, so this is the force, right? Pressure times area. And the only thing I'm Taylor expanding is pressure. So the area that this pressure is acting on is again ds dy with y perpendicular to the page. Here we have on this side P minus dps, the variation of P in the streamwise direction times the area that this pressure is acting on, which is dN times dy perpendicular to the face. That's the little cube face there, dN dy. And here we have P plus dps times the same area, dN dy. Those are all the pressure forces. I'm ignoring the two faces that are, parallel to my picture here. I'm just looking at this two-dimensional view of things. I'm just considering the extra dimension in the area as dy. That's all. I'm going to do streamwise and normal. So far, so good? Everybody follow me so far? Yes? Okay. So let's do the net force, the net pressure force in the streamwise direction. Pressure, streamwise. That's my little P and S indicate pressure and streamwise. So we have one force and another force. We have in the positive, we have P minus dps times dn dy. And in the negative, we have, in the negative S direction, we have P plus dps dn dy. So we can simplify. We have minus 2 dps times dn dy. But for dps, we've already written something up here, right? So we're going to use this here. And the 1/2 cancels with the 2. The minus remains, and we have minus dp ds times ds dn dy, which is the volume of the particle, the fluid particle, the volume of the fluid element. Now we have all the forces. We have the mass times acceleration up here. We have the weight and the pressure forces, and we put all of those together to write the force balance in the streamwise direction. So let me point those out to you because I'm going to have to clear the slide. We're going to put, so this is mass times acceleration. This is the component of the weight, and this is the pressure force. And these three are going to be the ones that contribute, the ones that need to be balanced out, right? Sum of forces equals mass times acceleration is what we're going to do now. Okay? Everybody ready for that? Okay, good. So, force balance in the streamwise direction. Sum of forces, all differential, all very small, but in the streamwise direction we have the weight in the streamwise direction plus the component of the pressure force in the streamwise direction has to be equal to mass times acceleration. But we already calculated these. The weight, we had well, let me write it out. D weight times sine theta. And then for these guys, we had minus dpds times the volume, right? ds dn dy. d oops. That is equal to, so for the weight, I'm going to write rho g, that is gamma, times the volume again. So I can put the volume outside and write minus gamma sine theta minus dp ds, and everything is multiplied by the volume, ds dn dy, and that has to be equal to mass times acceleration. So dm times the acceleration in the streamwise direction. So you see that the volume cancels out when I write here rho times volume, right? The volume will cancel out, and I could write minus gamma sine theta minus dp ds equals rho, the volume went away, times as, acceleration in the streamwise direction, which we already know is equal to v dv ds. This is now per unit volume. So the fluid particle's speed changes by a combination of the pressure gradient and the weight. which is kind of what we already knew from the hydrostatics, the extension of the hydrostatic equation to fluids with constant acceleration, if you remember. We had pressure gradient and weight. The minus gamma term is just weight. The only thing that we've done is that we're looking at this from in the streamwise direction, following a streamline. We've done everything in curvilinear coordinates, following a streamline. So now, note that we can write the sine of theta. So what is sine of theta? So if we were going in the streamwise direction, this was ds, and in the vertical direction we have dz, and theta was here, right? So the sine of theta is equal to dz ds. And we're going to do one really magic trick that is going to blow your minds. The fact that v dv ds, look at this, this is super clever, is 1/2 of dds of v squared. Wow. Get it? Simple, huh? Good. One mind blew. Why are we going to do that? Because then we want to integrate this equation. And now you see where this is going. I hope some of you might see where this is going. It's not going to be hard. This is just a clever trick. Let's call it the clever trick. You can't believe how much this clever trick is used in fluid mechanics. It actually comes up a lot. So now we're looking at variations along a streamline. So for the pressure, if we're looking only along a streamline, then we can write simply for dpds, we're going to just write dpds. We don't need to worry about the partial derivatives because we're moving, it's everything along a streamline. So we're going to just, and in this case, well, basically along a streamline, the differential normal is going to be equal to 0. So this is why we can do that. So finally we have then that this whole equation up here is minus gamma, sine of theta is dz ds, and minus dp ds equals to rho. Now we use our clever trick, 1/2 dds v squared. And this now can be integrated. Yes?
When did you start using C4? Because at first I thought you had the SDN and DY.
We're introducing it here with the purpose of getting rid of that angle.
So you just
No, n is perpendicular to the streamline. So these are curvilinear coordinates. So they're always changing with respect to your Cartesian ones, moving along the streamline. But z is always pointing upwards, opposite the weight. Gravity is always pointing in the same direction. Okay? But now, to integrate this, I'm going to, again, clear some space in my special way here. So now integrate. Well, first we're going to get rid of the ds and we're going to just write, let's see, we have dp. I'm going to put everything on the same side because these minuses bother me, so I'm going to put everything on the right. Okay, so we have dp, we have 1/2, well, let's see, dp, did I forget my rho? No, 1/2 rho dv squared and gamma dz equal to 0. So now I integrate these. Well, I'm going to divide by rho, okay? I'm going to divide over by rho and integrate. And so I'm going to have integral of dp over rho plus the integral of this is just 1/2 v squared. And here I have gz equal to a constant along a streamline. Now, if rho is equal to a constant, which, you know, incompressible flow, and then we get Bernoulli's equation, P plus 1/2, oh, where's my rho? Okay, 1/2 rho v squared plus gamma z equals to a constant along a streamline, which is Bernoulli's equation. Along, you see now how it's important to always apply Bernoulli's equation along a streamline. We did it sort of a little bit more leisurely by simplifying our systems where we just had a one-dimensional flow, basically one inlet, one outlet, and so we could apply this very, very easily. But then, and then we thought, okay, we'll apply this one inlet, one outlet idea to a stream tube, and we reduce that sort of idea to a very small tube, and then we use that along a streamline without really being very rigorous. This is the more rigorous way, and I would like to invite you to read some of the, or even just browse some of the articles that I've put on Blackboard for you. I mean, you can just type on Google misinterpretations of the Bernoulli, and you'll get a bunch of interesting articles about that. Basically, in the past, I would say 15 years, there's been a lot of chatter about this because there's a lot of physics books that are wrong in their interpretation of Bernoulli's equation. And even pilot's manuals sometimes have gone, because when people try to explain Bernoulli's equation, no, listen, here we've had to, you know, be trained in calculus to derive it this way, right? If you're not trained in calculus and somebody wants to explain Bernoulli's equation to you, they have to simplify things. And so in that process, somewhere it got lost in translation, is what happened historically, I think, right? Because you want to explain something without a calculus base, and people oversimplified things and started getting a little bit careless. So it's very interesting to read about those things. This is the proper way of deriving Bernoulli's equation. Now, we've done the whole thing for the streamwise direction, but we can also do it for the perpendicular direction, okay? Which is the additional thing that we can do now with this approach. And it's just a little bit more, and then I'll let you go to the next class. So let's look at that perpendicular direction. So again, the sum of forces in the perpendicular direction. Now we have normal perpendicular to a streamline equals to the mass of the fluid element times the normal acceleration, which is just centrifugal acceleration. So we have VR, v squared over r, and this is equal to, for the mass, we write density times volume, ds, dn, dy, and we have again the centrifugal acceleration, the component of weight, now is the minus weight times the cosine of theta. We can write this as minus gamma times the volume, ds dN dy times the cosine of theta. And the cosine of theta is going to be equal to now dz over dn in the same way as before. A little bit more work. I'm going to skip that. Then the pressure forces same as before. Now we had that little picture with all the 4 red arrows on the pressure forces. I'm not going to write that again. We're just going to try to remember it. And dF pressure, normal direction, is P minus dP normal times the area that it was being applied to was ds dy minus P plus dP normal ds dy. And so we have again minus 2 dP normal times ds dy. And here for this one we already had an expression. Again, the 2 cancels out, but the negative sign remains, dP dN times ds dN dy. So very similar to before. And we have the balance of forces, sum of forces, I think differential of forces I called it, in the n direction equals to the weight and the pressure forces, pressure normal, so that's minus gamma times cosine theta minus dP dN, all multiplied by the volume of the fluid ds dN dy, and that has to equal to the mass times the acceleration, which we also have up here, rho v squared over r times ds dN dy. The volume cancels out again. So the equation per unit volume now, and also substituting the expression for the cosine, is minus gamma dz dN minus dP dN equals to rho v squared over r. That is our equation for unit volumes. Now, for example, for gases, often we can neglect the weight so that we can interpret this a little better. Neglect the weight, and you see that dP dN in this case is going to be equal to minus rho v squared over r, which indicates that dP dN, if I have a curved streamline and I have I'm going to have a pressure that increases in the direction away from the center of curvature. So dP dN is in that direction, increasing away from the center of curvature, which explains our situation when you have a tornado. dP dN is going to be in that direction, which means the eye of the storm is the point of smaller pressure. You see? This equation perpendicular to the streamline helps us explain that type of pressure gradient. The pressure gradient due to the fact that the streamlines are curved. This is the situation of a tornado. The eye of the storm is the low pressure point. So basically dP dN in this case, dP dN you see here is balancing this pressure gradient in the normal direction, balances the acceleration due to the fact that the streamlines are curved. due to the fact that there's a radius of curvature here in the normal direction. And this is, you know, some a way to explain the pressure forces that we see, you know, in this type of situation. Here, if you twist, right, if you twist a fluid, you will see a minimum pressure being created at the center. The tornado situation and also the water funnels, there's a circular motion. The circular motion has associated to it curved streamlines. The centrifugal acceleration of the curved streamlines has to be balanced by a pressure gradient.